Greetings, and welcome to lecture number 9 on the course Introduction to Fourier Analysis. On the previous lecture, we applied our characterization of Sobolev spaces in terms of Fourier coefficients to establish the elliptic regularity theorem for Sobolev functions. This theorem stated that the solution G to an elliptic equation of order k, namely PD of G equals f, is k times smoother than the data function f of the equation. This result is neat, but a little unsatisfactory. The notion of smoothness is defined in terms of Sobolev regularity, and it is perhaps not so clear what this means concretely. We get a priori no information about the classical smoothness of G. For example, if f is C infinity smooth, is G also C infinity smooth in the classical sense? The purpose of this lecture is to answer this question positively. This is done via the following Sobolev embedding theorem, which states that high-order Sobolev regularity implies classical regularity of somewhat lower order. For example, infinite-order Sobolev regularity implies infinite-order classical regularity. The Sobolev embedding theorem is Theorem 2.8 in the lecture notes. It involves two natural numbers k and m, and we assume that k is strictly bigger than the ambient dimension d divided by 2 plus m. Then, briefly but inaccurately, the Sobolev embedding theorem states that the Sobolev space Wk2 of t is contained in the space Cm of t of m times continuously differentiable 2π periodic functions. This statement is inaccurate for the reason that Sobolev functions are a priori just elements in some LP space, and they are only defined Lebesgue almost everywhere. This is why one needs to be a little careful when making claims about the pointwise smoothness of Sobolev functions. The more accurate statement is the following. If f is a function in the Sobolev space Wk2 of t with parameter k as before, then f coincides Lebesgue almost everywhere with the function big F, which is m times continuously differentiable. To prove the Sobolev embedding theorem, fix a function f in the Sobolev space Wk2 of t, where k minus m is bigger than d divided by 2 as we assumed. The plan is simply to show that f coincides Lebesgue almost everywhere with its Fourier series, and then argue that this Fourier series defines an m times continuously differentiable function. For the purpose of differentiating the Fourier series, or any other series for that matter, we record the following calculus lemma, lemma 2.9, whose proof is left as a voluntary exercise. Assume that big G is defined as an infinite series of functions gi, each of which is individually m times continuously differentiable. Assume further that for all multi-indices alpha of order at most m, there exists a uniform constant c such that the sum over indices I of the absolute values of the alpha derivatives of the functions gi, evaluated at any point x in Rd, is bounded by c. Then the whole series big G is continuously m times differentiable, and the series may be differentiated term by term. The alpha derivatives of g are given by summing the alpha derivatives of the functions gi. We aim to apply lemma 2.9 to the Fourier series of f, namely big F equals the sum over all integer d tuples n of the functions hat fn times en. So let's check that this series satisfies the assumption of lemma 2.9 with the parameter m. As we have seen many times before, the alpha derivatives of the individual functions in this series are equal to I times n to the power alpha times f hat n times en. So we need to check that the series consisting of these functions is absolutely convergent as long as the order of the multi-index alpha is at most m. To this end, first note that the absolute value of the function in to the power alpha times f hat n times en is uniformly bounded from above by the constant norm of n to the power m times the absolute value of f hat n. Moreover, the sum over these constants turns out to be finite. Indeed, to evaluate the sum over all integer d tuples n of the numbers norm of n to the power m times the absolute value of f hat n, we first multiply and divide each term individually by the constant norm of n to the power k. We end up with the sum over integer d tuples n of the numbers norm of n to the power m minus k times the norm of n to the power k times the absolute value of f hat n. We estimate this sum from above by the Cauchy-Schwarz inequality. After doing so, we end up with the product of two sums, or actually the square root of this product, but this makes no difference for the finiteness of the result. The first factor in the product is the sum over integer d tuples n of the numbers norm of n to the power 2 times m minus k. This sum is finite by the assumption that m minus k strictly exceeds d over 2, or in other words 2 times m minus k strictly exceeds d. Verifying that this condition is sufficient for the finiteness of the first sum is left as an exercise. The second product is the sum over all integer d tuples n of the terms norm of n to the power 2 times k times the absolute value squared of f hat n. This sum is finite by the assumption that f is an element in the Sobolev space wk2 of t plus the characterization of such functions in terms of their Fourier coefficients, Theorem 2.6. We have now shown that the series of derivatives d alpha of the functions f hat n times en converges absolutely and uniformly for all multi-indices alpha of order at most m. Therefore, lemma 2.9 can be applied to differentiate the Fourier series big F, which was defined to be the series of the functions f hat n times en. The conclusion is that big F is an m times continuously differentiable 2π periodic function, and in fact the alpha derivative of big F could be written as a series of the functions in to the power alpha times hat fn times en, as long as the order of alpha is at most m. To conclude the proof of the theorem, it remains to show that the Sobolev function f coincides almost everywhere with the smooth function big F. This is simple. As a corollary of the estimate we proved earlier, we see that the sum of the absolute values of the Fourier coefficients of f is finite. Consequently, by proposition 2.0, the very first result on these lecture notes, f coincides Lebesgue almost everywhere with its own Fourier series big F. Since we just argued that f is m times continuously differentiable, this conclusion finishes the proof of the Sobolev embedding theorem, Theorem 2.8. We conclude the lecture by recording a couple of straightforward corollaries. The first one is the case where the index k in the Sobolev embedding theorem is equal to infinity. In this case, the inequality k is strictly bigger than m plus d over 2 holds for arbitrarily large numbers m. So we obtain the following corollary 2.10. The Sobolev space W infinity 2 of t is contained in a space of 2π periodic smooth functions. To be completely accurate, one should again write here that every function in the Sobolev space W infinity 2 of t coincides Lebesgue almost everywhere with a smooth function. The second corollary, corollary 2.11, concerns the solutions to elliptic partial differential equations with smooth data. Let P of d be an elliptic constant coefficient partial differential operator of order at least 0. Assume that the 2π periodic function g satisfies the equation PD of g equals f for some smooth data function f. Then there exists a smooth function big G which coincides with g Lebesgue almost everywhere. The proof is a combination of the elliptic regularity theorem, Theorem 2.7, and the previous corollary. Indeed, under the assumptions of corollary 2.11, the elliptic regularity theorem implies that the solution G lies in the Sobolev space W infinity 2 of t. Then, by the previous corollary, G coincides Lebesgue almost everywhere with the function big G in C infinity of t. Finally, as a concrete example of the theory we have just developed, let's point out that it applies to harmonic 2π periodic functions. Namely, let u be a 2π periodic L1 function whose Laplacian vanishes, in the sense of weak derivatives. As we pointed out in the previous lecture, the Laplacian is a fundamental example of an elliptic partial differential operator of order 2. Now, in this elliptic equation, namely the Laplacian of u is 0, the data function is the constant 0, which is certainly infinitely differentiable. Consequently, it follows from the previous corollary that any such solution u, which is only a priori an L1 function, must in fact coincide almost everywhere with a C-infinity smooth function. In other words, harmonic 2π periodic L1 functions are smooth. This concludes lecture number 9 on the course Introduction to Fourier Analysis, and also our treatment of 2π periodic functions and Fourier series. On the next lecture, we will get started with Fourier integrals and Fourier transforms. Goodbye for now.